In this video, we are going to be talking about how to determine the density of a gas. You might recall from an earlier chapter that density is equal to mass per unit volume. And I'm just going to write volume here as V. Mass is not in our ideal gas law equation, but mass is related to moles. We can obtain the mass of a substance by taking the moles, N, and then multiplying the moles by the molar mass. In order to cancel out the moles and get into grams. I'm going to use the symbol M, like a curly capital script M, for molar mass. So that when I rewrite this equation, I can take my density and then plug in, instead of where it says mass, I'm going to plug in N times my molar mass over V. Now N, it does appear in our ideal gas law equation. We know that N is equal to PV over RT. So now I can plug this where it says N. So now my density is equal to PV over RT times my molar mass divided by my volume. This volume will cancel out with that volume. And so now I'm left with my density is equal to my pressure times my molar mass of my gas divided by RT. So we can see from this equation that the density of the gas is entirely dependent on the pressure and the temperature, but the moles of gas and volume do not directly appear in this equation. So our density does depend on pressure, temperature, and molar mass, and the molar mass does depend on what the identity of that gas is. We can see that the density is directly proportional to the molar mass. So if the molar mass of our gas is larger, then that gas will have a larger volume, larger density than something that has a smaller molar mass. Let's do a practice problem. Without doing any detailed calculations here, which of the following gases would have the greatest density at STP? Go ahead and pause this video and think about that. Unpause the video when you are ready to check your answer. Okay, the correct answer here is krypton. And that's because krypton has the greatest molar mass out of all of these. Come on, why am I not writing? And so krypton has the greatest, come on. Krypton has the greatest molar mass out of all of these. The molar masses are displayed here. And we can see that krypton has the greatest molar mass. All of these gases would have the same, like if we had the same volume equivalent of all of these, 1 mole of each of these, then they would all occupy the same volume. But since they have different masses, they will have different densities. Here's a practice problem for you. Try to calculate the density of helium and nitrogen gas at STP. Unpause the video when you're ready to check your answers. Okay, so we have to remember what the definition of STP is. Our definition of STP is 1 atmosphere of pressure and 0 degrees Celsius, which is 273.15 Kelvin. So if I'm going to calculate my density is equal to my pressure times my molar mass divided by RT. So for helium, that would be equal to my pressure of 1.00 atmospheres, my molar mass of helium, which is 4.003 grams per mole. I'm going to use the R value associated with atmospheres, 0.082058 liter atmospheres per mole Kelvin. And then I'm going to use my temperature, which is 273.15 Kelvin. So when that's all typed into your calculator, you get 0.17859. And let's see, that has, well, unclear about sig figs, but I'll just have 3 sig figs. But so we'll say 0.179, and then it's asking for density. This is going to be grams per liter. So I got a liter here, and the grams, mole cancels with mole, atmospheres, Kelvin, Kelvin. So this is grams per liter. There is a second way of doing this. This is where units come in really nice and helpful. So since we are at STP, we know that 1 mole of any gas occupies 22.4 liters. That means if I take my molar mass and the molar mass as units of grams per mole, I can take this 22.4 liters per mole relationship. The moles cancel out, and then I'm left with grams per mole. And if you calculate the density in this way, we end up with the same value, which is really cool. Let's take that shortcut for our nitrogen gas. So for our nitrogen gas is diatomic, and so its molar mass is twice of 14, which is 28.014 grams per mole. And at STP, there will be 22.4 liters per mole. Cancel out the moles, left with grams per liter. And so take that 28 and divide it by 22.4, and you end up with 1.25 grams per mole. So if we compare the density of nitrogen and helium, we can see that this is less dense because it does have a lower molar mass than nitrogen. What's also cool about this is that means that balloons filled with helium float. And so that's why helium balloons float in air. Air is 78% nitrogen by mass, and so helium will float in air, which is mostly nitrogen gas. Balloons filled with carbon dioxide gas would not float. So if you blow into a balloon with your lungs, the balloon will not float in air because that's a higher molar mass than nitrogen gas. I just realized I wrote mole there instead of liters. Gotta fix that. That was a liter.